Hello, we finally reached uh, one of the most difficult topics in this sequence of lectures, the software and hardware solutions to the mutual exclusion problem. That is, how can we do synchronization with pure software, which means you don't need any help as long as you know how to write a program, even though there's no system support, you are still be able to write a program that supports mutual exclusion. Because this part three is rather difficult, my intention is cutting this lecture into three. The first part, try to build yourself from scratch, step by step, by going through a few simple examples, from very simple one to a somewhat sophisticated one. In lecture two, we will try to present you a correct algorithm. In lecture three, which is rather short one, we will discuss how to solve this the critical section problem, basically mutual exclusion, by the use of hardware. So, because this is an undergraduate course, we don't have to go through very deep results. We just want to know the basic concepts. As a result, we only focus on the solutions to two processes. That is, all the discussions in this and the next two lectures, there are only two processes involved. So let's say we have two processes, P0 and P1. By convention, if a process is Pi, the other process is always referred to as Pj, where j is 1 minus I. Therefore, if I is 0, then Pj is P1. If I is 1, then j is 0. So in this lecture, we will design some enter-exit protocols for a critical section in order to ensure mutual exclusion. As we mentioned earlier, we will go through a few unsuccessful attempts and finally yield a good and correct one. These solutions are pure software based. You can implement it in whatever language without any additional capabilities from the system. Before we go on, we have a very important assumption. This assumption is taken from Dijkstra's landmark work, Co-operating Sequential Processes. So the assumption goes as follows. Inspecting the current value of a shared variable and assigning a new value to such a shared variable are to be regarded as indivisible, non-interfering actions. In other words, in our terminology, they are atomic. That is, checking a variable's value and assigning a value into a variable, they are atomic, even though compilers may translate this testing or assignment statement into a sequence of machine instructions. For an example, suppose we try to assign a value I to a variable x, then generally we will load the value of I into a register and save the value in that register to X. So generally, we need two steps or two machine instruction I and J. But for our discussion, we assume that only one atomic instructions are there. With one instruction, we can do load and save. By the same reason, testing whether the value of X is equal to I, usually we have to load the value of I and load the value of X and compare. But our assumption indicates that we will assume all of this load and load followed by a compare to be executed in an atomic way. That is to save our time and to make our algorithm presentation easier. So as I mentioned, the meaning of this assumption is when two processes assign a new value to the same shared variable simultaneously, the assignments are done sequentially. Remember, atomic instructions are supposed to run in a sequential way. So suppose two processes, one tries to assign the value of I to X, the other tries to assign the value of J to X. They have to execute in a sequential way. Either we assign X to I first, followed by J assigned to I, or we assign J to X, followed by I assigned to X. Then checking the value of a variable and assign a value into the same variable. As we mentioned earlier, they are also atomic. But when a process checks the value of its shared variable with an assignment to it by the other one, the former, that is, process that does the checking, will find either the old value or the new one. We don't know which one is the correct one, or we don't even know the order. So these variables could be in register or in memory. However, always remember, expression evaluation is not atomic. Say, suppose we try to execute the following expression: a plus b is assigned to X. So a plus b is not atomic. It may translate to, say, load the value of A and load the value of B into a second register and add. But once you have the value, saving this value to the left-hand side variable, that is atomic. So remember this. So this is the original paper. I took it from the previously cited book. Dijkstra's paper was published a technical report, and then a paper sometime later. So we will show you several examples. For each example, we will examine whether it can implement mutual exclusion correctly, whether the progress condition is satisfied, and whether the bounded waiting condition is satisfied. In this lecture, none of the attempts will satisfy all three of them. So to make our discussion easier, we have the following assumptions about the behavior of the involved processes. The first one says, nothing is assumed about the remainder code except that it cannot influence the behavior of the other processes. In other words, in our program, we have the critical section code and the code elsewhere. The code elsewhere is referred to as the remainder or remainder code. So this remainder code of a process cannot influence the behavior of other processes. The second one says that shared object in an entry code and an exit code may not be referred to in the remaining code of a critical section. For example, suppose in the entry code or exit code, we use a variable I. Then in the critical section, you should not use this variable I. Basically put, the variables used in the entry section and the variables in the exit section should not be used in the remainder code of a critical section. The third one indicates that a process cannot fail or loop while executing the entry code, critical section, and the exit code. In other words, a process, when it is executing the entry code, the critical section, and the exit code, that process cannot fail or cannot do any infinite loop there. Why? For an example, suppose a process successfully executed the entry section and went into the critical section. So that means that process is executing in the critical section, and no other processes could be in the critical section corresponding to that one. Now, what if the one in the critical section dies or execute the infinite loop? Then nobody knows what would happen in the critical section. All the other waiting processes will see that, okay, that guy is still there. Now, if that process dies in the critical section, that process execution never reaches the exit code. As a result, the exit section does not know that process has died. Remember, the exit section, when a process executes its exit section, the exit section knows that process exits. As a result, the exit section must find some mechanism to inform the entry section, telling the entry section that the critical section currently is empty. Please allow the next one to come in. Now, if the process executing in the critical section fails or dies there, it's never being able to execute the exit section. As a result, the exit section cannot inform the entry section that the process was there, has exited, right? So this is very crucial. Then the next one is a process can take only finite number of steps in its critical section and exit code. In other words, a process should not have an infinite loop in the critical section and in the exit code. Otherwise, that process will never exit the critical section. Now, the next one is sort of explaining our practical practice. It says, while the collection of the processes is individual process or sequential, okay, the collection of processes in the critical section is concurrent. They compete to get into the critical section, but the individual processes are basically sequential. So let's try our first attempt. I'll try to be slow and ask you pause for a while to understand what's going on in a particular solution. So let's take a look at the process Pi. You just replace the value of I by J, and the J by I, you get it for the code of process Pj. So we have a shared variable term. This shared variable term could be anywhere as long as Pi and Tj would have access to it. And the Pi knows the value of I, its own ID, and the value of J, the ID of the other process. So I would just use I and J to represent this ID. So let me go through this program. First of all, we have a while loop. This while loop continually checking whether the current value is turned is not mine. Look here, Pi checks whether the value of turn is my value. So as long as the value of turn is not mine, so I keep looping here. Remember, this is a busy loop. It's a very tight loop, checking a very simple condition. As long as the condition is met, we loop. If the condition is not met, we break the loop. So this while loop indicates that. Let's check to see whether the value of turn is mine. If it is mine, I enter the critical section. Upon exit, I set your value to turn, meaning giving the critical section to you. So let me go through it carefully. This is a very simple solution. The entry section has only one statement, while. In the while statement, we use a busy loop, checking whether the variable turn has my ID, that is the value of I. If it's not, repeat and repeat and repeat and repeat. If the value of turn is mine, then I go into the critical section. Upon exit, I set the variable turn to J, giving the turn to you. So basically, the value of the variable turn serves as kind of a scheduler. If it's I, it's mine. If the value is J, it's yours. Okay, so please pause. Understand this very short code. Not only thinking about process Pi, but also thinking about process Pj. You have to think both processes in a concurrent way. So please pause. Before you can understand what's going on in this code, do not continue. I'm sure this is very simple code for you to understand, but please think in a concurrent way, thinking about Pi and Pj at the same time. Please pause. So when you come back, I'm sure you study this code because it's pretty easy. But you think it a bit deeper, notice the third bullet. Because after I exit, I give the turn to you. So suppose I serve as process Pi, you serve as process Pj. So if I am lucky, the current value of turn is I. Then when I execute this entry section, I found out the value of turn is mine, so I exit. Then upon exit, I give the turn to you by saving your value J into turn. Then when I come back, can I enter again? No, because in this time, the value of turn is J. So I will be looping here. When the value of turn can be changed, when you execute this while, seeing the value of turn being J, then you do the critical section and then you exit. Upon exit, you set the value turn to I, giving the critical section back to me. Even though you come back for the next try, Because you have already given the turn to me, meaning the value of turn is I. So you will be blocked here. Once you set the value of turn to J, when I execute this test, I will immediately notice that, oh, turn is mine, so I could enter. Therefore, this kind of execution would force you and me to execute in an alternating way. I finish the critical section, then giving the turn to you. Then I wait with a busy waiting here. Then you enter, you exit, and at the same time, you give the critical section back to me. Then if you return to here, you wait and I enter. So isn't it I, J, I, J, I, J in this alternating order? Please stop and think about it. If you have question, rewind and rewatch this very short explanation. As I mentioned, I will ask you to stop several times because I found out this is very helpful. Then, after understanding what's going on in this program, we're going to look at whether the solution satisfies the mutual exclusion, the progress condition, and the bounded waiting condition, even though we know this is not a very good algorithm because it enforces the execution in an alternating way. But it's a good practice. Now, remember, in the previous lecture, I asked you to refresh your knowledge in the proof by contradiction. The proof by contradiction goes as follows. We have an assumption in order to derive a conclusion. Proof by contradiction assume that the assumption is wrong. And then we derive something absurd. Then we know if something absurd occurs, that means our assumption is wrong. Therefore, the conclusion has to be correct. So for two processes, the proof for mutual exclusion is usually done by the proof by contradiction. This is the easiest one for you to prove mutual exclusion. For progress and the bounded waiting, it's not so. But I want you to learn how to prove mutual exclusion, the easiest part. So how do we do that? I will repeat this pattern over and over. Hopefully, you'll remember it. Don't blame me for repeating too much because some people need it. So how do we do that? Read the program for PI, forget about PJ. Read the program for PI and find out in what condition PI can be in the critical section. Write it down. Okay, so reading a short program properly is so important when you want to prove mutual exclusion. Again, find the condition for PI to enter the critical section. While you are doing this, forget about PJ. So now let's try. If PI, let's say just use P0, okay? Or PI, it doesn't matter. So PI would wait here. When the value is turned, changes to I, PI enters the critical section. Do you remember this? So immediately we notice that PI is in the critical section if and only if the value of turn is I, right? Because this is the only condition that could block PI to enter. So we found the first condition. That is, PI is in its critical section. I use CS to indicate the critical section. If turn is I is 0. Do you get it? Now, switch to PJ. Change the value I to J, the value I to J, and the J to I. So PJ would wait here. This is the protocol, the intersection. Now PJ continually checks whether the value of turn is J. If it's not, wait. This is BC waiting. Now when the value of turn changes to J, PJ enters. So we are able to find the condition for PJ to enter. So the condition in this program, because it's symmetric, so the condition for PI to enter, the condition for PJ to enter are essentially the same, except the values are different. So let's get the second bullet. PI is in its critical section if turn is I. Now PJ is in its critical section if the value of turn is J. So we have found the conditions for PI and PJ to enter. Now we play the proof by contradiction game. Remember, mutual exclusion means at any moment, there is no more than one process in the critical section, right? So its opposite is we have two processes, PI and PJ. Both of them are in the critical section. This is the contradictory assumption. We want to prove only one can be in the critical section, but to prove by contradiction, we assume both are in the critical section, and hopefully we are able to derive something absurd. So if PI and PJ are both in the critical section, this condition is true for PI, this condition is true for PJ, right? Therefore, turn is equals to I and the turn equals to J are both true. Can you get it? If you can't, let me try again. We know PI is in its critical section, then turn must be I. Condition for PI. Condition for PJ is if PJ is in its critical section, then J turn must be J. Now, we try to use the proof by contradiction technique. We assume both processes are in the critical section, and hopefully we are able to derive some absurd results. As a result, because if the assumption is both processes are in the critical section, but we get something ridiculous. Therefore, both processes cannot be in the critical section at the same time. This is the proof by contradiction technique. So if both processes are in the critical section, this condition is true for PI, this condition is true for PJ. So that means turn is I and the turn is J must both be true. So if turn equals I and the turn equals J are both true, what do we get? It means the variable turn holds the value of I and J at the same time. Now, if we return to I being 0, J being 1, then the variable turn must hold the value of 0 and 1 at the same time. Is it possible? No. In conventional computer, this is impossible because a variable can only hold one value, either 0 or I. Although in quantum computer, a quantum bit could hold two values, but we are not talking about quantum computers here. We base our discussion on traditional computers. So if both processes are in their critical section, then turn equals to 0 and turn equals to 1 must be true at the same time, which means the variable true turn holds two values, 0 and 1, which is impossible. As a result, both processes cannot be in the critical section at the same time. So please pause and understand what I said in the past few minutes before you continue. This is your first encounter in using the proof by contradiction technique to establish mutual exclusion for an algorithm. Please pause. You could repeat this several times. Now, when you are back, I assume that you know how to prove mutual exclusion for this very simple algorithm completely. Then let's move on to the progress condition. Remember what progress condition means. The progress condition has two subcomponents. The first one is referred to as the outsider issue. If some processes are waiting to enter a critical section which is now empty, so the algorithm must pick a candidate to enter, and only those who are waiting to enter can participate in this competition. No other processes that are not interested to enter could influence this competition. This is the first part. The second part states that this decision for selecting a candidate to enter must be done in finite time. Okay, so let's see whether the progress condition is met. So let's say, always remember, this algorithm, as in on the first slice of attempt 1, it enforced the order of 1, I, J, or process 0, process 1, process 0, process 1. So what if process 0 is waiting here, or process I is waiting here because I use I, process I is waiting here, and process J is elsewhere. That's not executing this while loop. Of course, process I and process J could execute the while statement at the same time because the value of turn can only hold one value. Then one will get in. We don't know which one because that depends on the value of turn. Now, what if PJ is not waiting and elsewhere executing something else? So in that case, the value is cannot be reset to the value I, which you need here. So that means PJ gets its turn because the value of turn is J. And PJ executes its critical section. Upon exit, PJ set a turn to I and go elsewhere. So if you are here, that's fine. And then you get in, right? Now, what if after getting, you set the value of turn to J, that's yielding the critical section to J, and then you come back. Because you just set the value of turn to J, this condition is always false. So you are looping here. So what if PJ is not interested to get in at that moment? So PJ, the execution of PJ actually influences whether you can get in or not. Therefore, an irrelevant processes blocks other processes from entering a critical section. This is not good, of course. Therefore, the first component of the process progress condition fails. Now let's look at the second component, although it's not on the slide, but it's so easy. What is the second component in the progress condition? You'll have two processes waiting to enter. That is, we have only two processes. The PI and PJ are both waiting to enter, which means PI is executing this while PJ is also executing this while in its address space. Now, the decision time is how long does it take for either PI and PJ to enter, right? The second component of the progress condition indicates that this has to be done in finite time. So let's say PI and PJ are waiting to enter. Both are executing this while statement. Because the value of term can only be I and J. So one of these two processes will see this condition being false. The other process will see this condition being true, of course. Then that process enters. So testing whether this condition holds or not is the process to pick a candidate to enter. So the time spending on picking a process to enter is the time to execute this condition. Execute this comparison is, of course, finite. Right? There's no loop there. So however you transit it to a set of machine instruction, the time needed to execute this finite number of comparison instructions is always finite. Therefore, for the progress condition, the second component, that is the finite decision time, holds. So for this algorithm, we are fine with the finite decision time, but we're not fine because an irrelevant process could affect the decision making here. So actually, and precisely to say that is, the progress condition fails. So my question is, does bounded waiting hold? Bounded waiting means when I want to enter, you have to find a bound. I wait here only that no more than that number of processes could be ahead of me. Say, suppose the bound is 3, then that means 3 processes could get through before I can enter. That is the fourth. I am the fourth process to enter. So think about it. What is the bound? And if this algorithm satisfies bounded waiting. Now, if it does not satisfy bounded waiting, the value of bound doesn't make much sense. So this is an exercise. Study this algorithm carefully and make sure whether this algorithm satisfies the bounded waiting condition. If it does satisfy the bounded waiting condition, what the bound is. Okay, so please pause and make sure you understand the discussion of the progress condition. You may do it after watching this video for the bounded waiting condition. Please pause before we try attempt 2. Now, let's look at attempt 2. It's a completely different algorithm. Later on, we will combine attempt 1 and attempt 2 to a much better algorithm, and then finally, we reach a correct one. Going through this process, although lengthy, you will learn a lot of it. So This algorithm uses a Boolean array. You could declare this an integer array of 2 elements, both initialized to false. The algorithm is pretty simple. Say pi says I set true to flag I. My flag I is used by pi. So pi set true into flag I, saying, oh, I am interested. And wait for you until you are not interested, or saying it in a slightly different way. The intersection goes as follows. I am interested. As long as you are interested, I loop. Now, if I loop here, I won't be able to enter the critical section, right? So, very interesting implementation. I set myself to I am interested by saving true to flag I. And then look at your flag. As long as you are interested, I wait. If you are not interested, I get in. Upon exit, I set my flag to false, meaning I am not interested at this moment. Of course, sometime later, I may come back to enter the critical section again. In this case, I set myself to be interested and check to see whether you are interested. If you are interested, I wait. And if you are not interested, I enter. So again, we use a busy waiting here. We have seen it in attempt 1. We also see it in the shared memory discussion. So study this algorithm before you continue. This flag variable is global. Please pause. Again, we will investigate mutual exclusion, progress, and bounded waiting. The procedure for proving mutual exclusion for 2 processes is almost by contradiction. So this is why in early lectures, I strongly encourage you to refresh your knowledge in proof by contradiction. And if you are not used to it, attempt 1, I went slowly. I'm going to do it slowly again. So look at here. Let's study what is the condition for process 0 to be in its critical section. Now, look at the code again. P0 set true to flag 0, indicating I am interested. And P0 keeps looking at your flag, that is flag 1. As long as flag 1 is true, P0 simply loops until flag 1 is false. Then P0 enters. Now, just warn you, these are simple examples. While you are reading the code for P0, you could simply ignore P1. By the same reason, while you are reading P1, in order to find the condition for P1 to be in its critical section, you just forget about the code written for P0. So we can easily find out P0 is in the critical section. Flag 0 is true, flag 1 is false, right? Flag 1 P0 is here, flag 0 is true because it's never modified after setting it here. And flag 1 has to be false in order to break this while loop. Therefore, we know P0 is in its critical section if flag 0 is true and flag 1 is false. Now, let's change the role to P1. Replace I by J, replace J by I, okay? So let's take a look at this. Now we act as P1. So P1 set true to flag 1. And P1 checks to see flag 0. As long as flag 0 is true, P1 waits with this busy loop. Once P1 sees that flag 0 is false, then this while loop breaks and the P1 gets in. So by the same reason, P1 is in this critical section. Flag 1 is true. Flag 0 is false, right? So stop for a while and figure out why I get these two conditions, even though it's very easy. P0 is in its critical section. If flag 0 is true, flag 1 is false. Read the code for P1. P1 is in its critical section. Flag 1 is true, flag 0 is false. Okay? So let's follow the same trick. We assume that P0 and P1 are in the critical section at the same time. Therefore, this condition and this condition must be true at the same time. If these two conditions are true at the same time, it means flag 0 is true and flag 1 is false, and flag 1 is true and flag 0 is false must be true at the same time. Now, if we look at flag 0, from P0, flag 0 is true. From P1, flag 0 is false. So if both conditions are true, flag 0 must be true here and must be false here. But flag 0 is just a variable. A variable can only hold one value. As a result, flag 0 cannot be true and false at the same time. By the same reason, flag 1 is true, is false here. Now, if P1 is also in the critical section, flag 1 is true here. So if both conditions are true, flag 1 must be false and true at the same time, which is absurd. As a result, if we assume that P0 and the P1 are both in the critical section, then flag 0 and flag 1, each of which must be true and false at the same time. That is absurd, impossible. Therefore, our assumption that P0 and P1 are in the critical section at the same time is wrong. Consequently, only one process could be in its critical section. So please go through this slide and pause, make sure you understand this proof completely before we go on. Please pause. Then the next attempt would be, is the progress condition true or false or partially true? Remember what a progress condition is. It consists of two components. One, the outsider. That is, the irrelevant process cannot have any influence upon the selection process for selecting a candidate to enter the critical section. Component 2 states, if we have multiple processes waiting to enter the critical section, the entry section must be able to select a candidate to enter in finite time. Okay? Now let's examine the outsider issue. Let's say if P0 wants to enter, P1 is not interested to enter. Now, because both flags are initialized to false, and P1's flag was set to false upon exit. Then, when process 0 wants to enter, process 0 will see flag 1 being false. Therefore, process 0 can enter. Remember, the flags were initialized to false. Now, if P1 is not interested, when P0 reaches here, flag 1 is false, so P0 enters. No matter where P1 is, as long as P1 is not here. Therefore, an outsider, P1, will not have any influence upon the decision-making of selecting a process. So component 1 is good. Although I did not put it here because it's easy to state and easy to prove. Now, how about finite decision time? Remember what the finite decision time component says. It says when the critical section is empty and both processes want to enter, the entry section must pick a process in finite time so that the candidate would enter. Recall this. And if you could not record it, let me say it again. The second component is the finite decision time issue. When both processes are waiting to enter and the critical section is empty now, then the enter section must select a candidate to enter in finite time. We don't know which one, P0 or P1. As long as one will be selected in finite time, that is fine. Okay? Now, this is something you have to have your concurrent in mind in order to understand it. Why? Let's say I am process I, you are process J, okay? I am process I, you are process J. Now, what if you and I approach the intersection at the same time? I put true into flag I, and you put true into flag J so far. Fine, right? And then we'll move on to the next step. Checking to see whether your flag is true. Of course, you just set your flag J to true, and you are checking to see whether flag I is true. Then both of us would be stuck in this while. Both of us would have no chance to break, because right after setting this flag, neither you nor I would be able to reset the flag to false, right? Therefore, after setting this flag, our flag to true, both of us would be looping here. It won't be able to select either you or me to enter the critical section in finite time. Therefore, in this solution, the second component, finite decision time, fails. Think about this. So far, we studied the progress condition. The first component, outsider influence component, holds. But the second component, the finite decision time component, fails. Now, please pause and think about it before we move on to the next one. Okay, let's study bounded waiting. Let's say Suppose PJ is in its critical section, and PI is waiting to enter. PI is waiting to enter. PJ is in the critical section. Now, the key fact is, if PJ is in its critical section, flag J is true, right? Because flag J was set by PJ here. So if PJ is in its critical section, flag J is true. As a result, PI will loop here, right? Now, upon exit, PJ will set flag J to false. So far, so good. So the question is whether process I could see the change of flag J. You may want to say, of course it could. Yes, it could, but it may not have this chance. For an example, suppose PJ was here and set flag J to false while process I is testing flag J. But it's very likely that this while statement checking is still a while statement. Look at its value in an atomic way. And if this true, go back. So there is a context switch happening after you checked, you've done the first check. And before you are able to go back for the next check, process J comes back so fast and set flag J to true. So the next time when you go back to check flag J, whoops, it's already changed to true. Can you follow me? If you can, let me try it again. So suppose I am here. I play this process J. You are process I. So I am here. And you try to enter. You set your flag to true and look at my flag. Because I am here, of course, flag J is true. So you are looping here. So this loop, even though checking the value is atomic, but after checking this value, you see it being true, then you have to go back for your next checking, right? So upon exit, you just check this value of flag J, seeing it being true, then I set to false. Before you can check it again, I come back. Set my flag J to true. And then you are able to look at it again. What value you will find out in flag J? Of course, true. So you're stuck here. Now, because you have already set your flag I to true, when I come back, I can at best set flag J to true. And then I will find out your flag I is true. So we return to the indefinite decision time. Do you get it? So that illustrates a very interesting fact, as we discussed in the last lecture. As I mentioned, progress does not imply bounded waiting, and vice versa. So this means it's very hard to establish bounded waiting for this attempt. So please stop here, because the next one is more complex. Okay, so before you stop, let me inject some thoughts here. Why we have this situation? I exit and I could come back very fast, and then you and I are stuck here. So we have to find some way so that none of us would be able to stuck here forever. In other words, we are able to play a nice game. A nice game. Oh, while I see, okay, you are busy. You have your flag false. How about this? I yield. I so far I'm not interested. I am not interested. Waiting to see you are not interested, and then I become interested again. This is a very simple thought, but forget about here. Just a hint. Make sure you understand what I said. This is very difficult to establish bounded waiting for this algorithm. Please pause. Now, this is our third attempt. Excluding this box is essentially the previous algorithm, right? Set my own flag to true and test to see whether you are interested in. If you are not, then I go in. So we add this component. This component is what I said. We duplicate this part so that I make sure I am interested, but as long as you are also interested, I try to give up and retest the condition for me to enter. And if the condition, after checking the condition, okay, you are not interested, then I indicate I am interested again. But I cannot get in because you may be so fast. Remember the previous attempt. So after setting up, I am interested, I go back and check to see whether you are interested. So we actually have two sets of tests. I am interested. Are you interested? Or I am interested and go back. Are you interested? And if you are interested, or you may be in your critical section, of course, then I say, oh, okay, I am not interested so far, and wait for your turn. Until it's my turn, I set my flag to interested. So upon exit, it's all the same. The only modification to this attempt 3 is we add the double checking. The first check is here. This is my checking whether you are there or not. Because if you are not there, you set the flag to false. And if you are there, I wait. And if you are there, I simply go in. So if you are there, then I cannot do anything until you are gone. Therefore, I say, okay, I'm not interested. Wait for you to be gone. Now, once you set yourself to be I'm gone, then I reinitialize this sequence. Interested? Are you interested? Or interested? Are you interested? So the flag values are initialized to false. Now, please study this algorithm before you continue and understand why we add this part. Previously, without this part, it's just a hint. You and I could be stuck here forever. Now here, why? We won't be stuck here forever, but there is still some risk. We will discuss later. So please pause. So as you can see, these programs are all simple. Probably just a little bit more complex than an infinite loop. But reading the simple program effectively is important to your success. And this is why I use so many examples in order to help you to understand how to prove mutual exclusion in particular. So remember, I am interested. Test to see whether you are interested. If you are not, I enter. Upon exit, I say I am not interested. Or if you are interested, it means you are in the critical section. That I will say, okay, I am not interested, and wait for you to exit. Upon exit, then I re-indicate I am interested and go back to test it again. Why I cannot go in here? It is because you may run so fast. Once I found out, okay, you are not interested, then if I try to get in, but you, and unfortunately, there is a context which happens here, then you may go, you could have gone back and test to see whether I am interested or not. Because I haven't been able to set my flag to true here, then you may go in immediately because my flag was set to false here. So this is what I want to indicate or a hint for a progress and boundary waiting. But so far, let's concentrate on mutual exclusion. Again, how to prove mutual exclusion is rather simple. It's rather simple. Read PI's code. Get a piece of paper and pencil. Read the code for PI and find out what makes PI in its critical section. Now, I hope you will not read this part and follow my discussion, or I am sure Michigan Tech students are very good. I'm sure most of you could immediately figure out what would make PI to be in its critical section. So PI can be in its critical section if and only if this while loop breaks, right? No other way PI can reach its critical section. So if this while loop breaks, it means flag J is false. Do you get it? So let me quickly go through it. PI is in its critical section if and only if this while loop breaks. And this while loop breaks if and only if flag J is false. So we know part of it. But we need more. If PI is in its critical section, flag I is set to true. So far we know process I is in its critical section. Flag I is true. Flag J is false. I hope you agree. But is this complete? I'm afraid to say that no. The reason is if the execution goes as follows, the first time you set here, the first time you set flag J, then you go into here, that's fine. Flag I is true, flag J is false. But if when you did this flag test, flag J is true, then you go into here. And then in this in the body of this while, you set flag I to false, and then do here, and then reset flag I to true. So there are two places for you to set flag I to true. So no matter what, flag I has to be true here. Either you go here and for your first test, and then the execution flow goes here. Then flag I is true. Or you set flag I to true and sees that flag J is false, and you do this, and then you reset flag I to true and go back several times until you see the value of flag I is false, then you go here. This is a complete discussion for the condition of PI being in its critical section. what this condition is, no matter the first time you check and you get the program flow here, or you probably repeat here several times and then you go here. So the condition is if PI is in its critical section, flag I is true, flag J is false. Do you get it? Now, if PI and PJ are both in its critical section, then flag I must be true and false. For the same reason, flag J must also be true and false, as we discussed for attempt 2. Do you remember that? Therefore, flag I is a variable and flag J is a variable. A variable can hold two values, true and false. Therefore, we reach a contradiction. That is, we assume that both processes being in its critical section is false. It cannot be true. Therefore, either P1 or P2 is only one process, or at most one process could be in its critical section. So please pause before we continue. Then let's study progress. Again, hope you don't blame me for regurgitating everything, because that's a good way for me to remind you, and also a good way for you to remember something. What is the progress condition has two components. The first one is the outsider influence issue. That is, when a decision is making in order to allow, in order to select a process to enter its critical section. Only those who are waiting can participate in this competition. Those who are not waiting, the outsiders, cannot have any influence. So let's try to see how, whether outsider issue is true for this argument. Because this argument is just a simple modification by adding something here. You can expect that the outsider influence condition is met, because upon exit, process I or process J will set the flag to false. The other process waits here will see, okay, the guy just changed flag to false. Therefore, because that guy's not waiting, nowhere to be found in the entry section. Therefore, I can enter. Therefore, we know in a process that is not interested to enter, that's in this section, would not have any influence upon selecting a process who is waiting here. That's easy. I hope you can follow me. Now, the next one is, again, finite decision time. Finite decision time means both processes, Pi and Pj, are waiting to enter, and that no one is currently in the critical section. Then, can we show that in finite time, I am able to select a process from either Pi or Pj to enter? As you know, when you look at this type of program, usually when both processes Pi and Pj run in a synchronous way, you have trouble. Now, let's say I act as Pi, you act as Pj. So you and I execute the same statement. I do this setting true to flag I. You also set true to your flag J. No problem. And then we execute this while. I see your flag being true, and you see my flag being true. So both of us enters the while loop. And then I set my flag to false, you set your flag to false. And then both of us executed in a while. I see your flag to be false, and you see my flag to be false. So both of us break this while loop, and both of us set the flag to true, and we go back. So we don't know how much time is needed in order to selecting either you or I to enter. Theoretically, this fully synchronized loop can go again, again, and again, and never ends. Therefore, the decision time depends on the execution time of this while. But the execution of this while, as we just mentioned, could be infinite time. Therefore, the second component of the progress condition fails. So again, this algorithm even modified by giving the decision to have a second chance. The progress condition still holds 50%. Outside the issue, okay. Progress, the finite decision time issue, sorry, fails again. So please pause and make sure you understand this part. Now, when you are back, in attempt 2, it's very hard for us to establish the bounded waiting because both processes could be stuck in the intersection. Now, after adding this part to try a second time, would this resolve the bounded waiting issue we learned in attempt 2? Let's try. Now, let's say if process I or 0 set the flag to false, then the outer process P1 has a chance to break its outer loop here, right? And after P1 sets its flag J or flag 1 to false, then either P0 could break this while loop or this while loop. That's our original thinking. However, it is possible before flag 0 is set to true here, and P1 comes back after exit so fast, and it sees, okay, flag 0 is false, then I could enter. Let me quickly go through it. P1 is here. So P0 has flag I true, and flag J is definitely true because flag J is here. So PI reset flag I to false. Fine. And because currently PI is still here, so P0 will loop here because flag J is false. Flag J is true, sorry. Then upon exit, PJ sets its flag J to false. Now, right after flag J is set to false by PJ, P0 may be able to break this while loop, right? That's no big issue. But what if we have a context switch here? After PI sees flag J being false and breaks the while, the execution of PI is suspended. And the PJ is a very, very fast runner. So after setting flag J to false, PJ comes back, setting flag J to true, and sees flag I. What flag I is? You just set it to false. Therefore, PJ has no obstruction. It simply goes into the critical section. After doing it, it set the flag to false and goes back and set the flag J to true, and see your flag is false because it's here. So you never know how many times PJ can have access to the critical section before you could set flag I to true. This is the issue. Hopefully, you could understand it. You may want to try, go through it several times, but don't worry. I have an execution sequence here. Always write your execution sequence in this way. Here, I use F for flag. So, in an execution sequence, you have to involve the processes P0 and P1. And the value of for flag 0, the value for flag 1, and some comments here. Sometimes I drop the comments because I don't have space. The screen space is quite limited. So both processes starts. They set their flag to true, look at here. And then process 0 checks your flag, process 1's flag. So enter here. And then process 1 executes its while loop. So because at the same time, you set your flag to false. So flag 1 enters immediately. And for you, your P0, after setting your flag to false, then you see my flag being true. So you looked here. Now upon exit, I set my flag to false, then you reset your flag 0 to true. And simply doing this interleaved execution, I may be able to going in and out so many times, but you don't have any chance. Or as what I said, there could be context switch here. Before you can set your flag to true, I exit and go back so quickly because you haven't had any chance to set your flag to true. When I test this flag, of course I can go in. So this execution sequence is different from what I said with respect to context switch. But this context switch is probably easier. But this one shows to you, even though without a context switch concept, you can still find, or you can still construct a execution sequence like that. Okay, this is long enough for this lecture. In the next lecture, we will discuss more algorithms toward a correct and a very, very simple one. I hope you'll study these 3 attempts before we go for the next lecture. So hopefully you will learn how to prove mutual exclusion, progress, and bounded weighting through these 3 attempts. So let me stop here. See you next time. Goodbye.